Okay, so here is my video on effect sizes, type 1, type 2 errors, and power. So effect sizes, what we're going to start with. So your effect is how big? So when we're talking about effect sizes, we're really talking about the difference between practical versus statistical significance. Okay, so whenever we start talking about significance, people tend to think of it first as practical significance, but we've been using it in this alternative way, statistical significance. So statistical significance is really when we make that decision. Are we going to reject or not reject the null hypothesis? So statistical significance refers to the decision that we make based on the odds or probability that a particular sample or observation could have happened by chance. This is what we've been using so far in this class. This is what we've been talking about and focusing on as far as hypothesis testing. So when we reject the null, we say it's significant, statistically significant. When we don't reject it, we say it's not statistically significant. Now, that's different from being practically significant. So practical significance is what you really think of that word, significant, right? So when something's practically significant, really it means that we can use that result in some way, or it is an important result, or it's interesting, or it has an application in the real world, right? So probably what you think, like practically, it's significant, it's interesting, which is different from statistical significance. And the way that we really measure or quantify practical significance, how practically significant something is by using measures of effect size. So effect size is literally how big is the effect that you're looking at. So if you're talking about differences between means, we want to know how big is the difference between means. Is it really big difference or is it really small difference? How strong is a correlation if we're talking about relationships between variables? Are two things very strongly correlated, very strongly related, or are they only weakly related? Right? So when we talk about small, medium, large correlations, or weak, medium, or strong correlations, we've already been talking about effect size. Now you can express effect size in terms of like the raw numbers that you're working with. So for example, if we're talking about differences in IQs, we could just say that university students have a mean IQ that is 20 points higher than the general population. That whole 20 points higher, that gives us some measure of effect size. Tells us 20 points, right? Tells us how big the effect is. Where this is a problem is when we have different studies that use different ways of measuring something. So what we typically tend to do when we talk about effect size is we tend to use what we call standardized effect size. So this means that we convert the raw units into some kind of standardized way of measuring it so we can compare across different studies even if people measured something a little differently. Some common statistics or common standard effect sizes that we use include R for correlation. Remember we talked about, is it a weak correlation, a strong correlation? We also use R squared in regression. So when we covered regression, we talked about the R squared tells us basically how good is the model. Is it a really, really good model where it explains a lot of the variance? Or is it a pretty bad model where it doesn't really explain very much variance? We're also going to refer to this one here. It looks like a weird N. That's called eta. So eta squared is what we talk about when we do ANOVA, which is going to be our next topic after t-tests. And Cohen's d is typically what we use when we talk about the difference between means. So in terms of these, d is the most widely used effect size when we talk about differences between means. And R is the most widely used effect size when we're talking about relationships between variables. So to show you kind of a visual of what Cohen's d is actually doing or how it's calculated, it really depends on how much overlap there is between the two groups that you're looking at. So we can see in this top part of the illustration, there's a ton of overlap, right? Everything that's kind of in this section is overlap. And there's very, very little of this orange part and this kind of purpley blue part that isn't overlapping. So this reflects a really small effect size because the means, if we were to find the mean of this kind of orange curve, and the mean of this bluish curve, that difference is really small, which means that most of the people in the orange curve and most of the people in the blue curve tend to have about the same scores, right? There's only this little sliver of people who are different on this side and this little sliver of people who are different on this side. So Cohen's d of 0.2, you can see in our table 0.2, that means that there's only about less than 15% of our people in our groups that are not overlapping each other. They don't have similar scores. So this is what we would call a small effect size. So anything below 0.2, we basically would say there's no effect. Anything with a Cohen's d of 0.2 all the way up until 0.5 is a small effect. From 0.5 up to 0.8 is a medium effect. Anything bigger than 0.8 is considered large. And if you get over 2, that's really large. Right? So we can see in this case, the second one with 0.5, this is kind of the bottom of what we can consider a medium effect size. So the differences between our means is about this big. And we can see with a 0.5, we have about a third of the points do not overlap. So if you consider this chunk here and this chunk here, that represents about a third of all the sort of scores that are represented in total. Here we see a Cohen's d of 0.8. That's the minimum of what we would consider a large effect size. And so you can imagine as these two curves sort of move apart, the effect is getting bigger because that difference between the means is getting bigger and bigger and bigger. So if we had something like a 2.0, really big, we would expect to see curves that are really far apart and have a lot that does not overlap. All right. So now that we sort of talked about what effect sizes are, I'm going to refer to those in this next section when we start talking about mistakes, because nobody's perfect. So in terms of statistical significance, so switching back away from practical to significance to what we've talked about before, statistical significance. So here are our rules for deciding on if something is statistically significant or not. And hopefully you know this by now. So if our p-value that's produced by PSPP or Excel or SPSS or whatever, if you're doing it by hand, if that p-value is less than our significance level, which is usually alpha of 0.05, then, so if our p is less than 0.05, then we would say that the result of the test is statistically significant, and we would reject the null hypothesis in this case. If that p-value that we get is higher than our significance level, if it's greater than 0.05, this is when we say the result is not statistically significant, and we do not reject the null hypothesis, right? Do not reject. So here we have p less than 0.05 versus p greater than 0.05. So again, hopefully that's a little review. So let's take a closer look at when we're making this decision to reject or not reject. So let's say that we do reject the null hypothesis. Okay, so this means that our p-value was less than 0.05 and we say that's significant, I'm going to reject the null hypothesis. That guy's out of here. Now it could be that, great, there really is some effect. There really is some difference in the means or some relationship there. AKA, it's good. The null hypothesis is not true. There really is something going on. And so if we reject that null hypothesis that is not true, then we're making a correct decision, right? Yay. Yay for us. We did the right choice. However, there's always a chance that we are making the wrong decision. So it could be, yes, there is an effect and we found it. But it could be there really is no effect there and we made a mistake. We found something by mistake that doesn't really exist. It's just a really, really weird sample. So in that case, we call that a type 1 error. Type 1 error is where we say, I found something. There is a significant effect. There's a significant difference. There is a correlation, but really there's not. All right, so just because we get a significant result does not guarantee that there really means there's an effect. We could always be making this mistake, a type 1 error. Now, type 1 error is associated with our alpha level, and we'll kind of come back to that. So that's if we reject the null. Let's look at the case where we don't reject the null. Our P was above 0.05, and we're like, oh, well, they're not statistically different. They're not significant, not different. There's no real correlation going on there. And we don't reject the null hypothesis. Now, just like when we do reject the null hypothesis, this doesn't necessarily mean that the null hypothesis is absolutely true. Oh, we got P equals 0.653. That's not significant, so the null hypothesis has to be true. That's not the case. It doesn't have to be true, right? What that means is that we don't have good enough evidence to think it's not true. It could not be true, but we can't see that based on the data and the evidence that we have, right? So we have to not reject it. So in other words, what it means when we don't get a significant result, right, when we don't reject the null, is that either it's true, there really is no difference, there really is no relationship, nothing interesting is happening, the null hypothesis is really true, and again, we made a right decision because the null hypothesis is true and we said don't reject it, keep it, right? So if it's true and we keep it, those two things go together. So that's correct. Again, yay for us. However, we could have made what's called a type 2 error. So a type 2 error is where you say, I didn't find an effect, there's no effect. But really there is an effect somewhere, we just missed it. Our data just wasn't good enough to see it. And so we weren't confident enough to say reject it. And so we kept it when we really should have rejected it because there really is something going on. Okay, so that's called our type 2 error. So let's put this in context of like the different options, different decisions. And I'm going to do a little visual in a second. So I set up this kind of 2x2 table. So on the top here, we have the true state of the world, right? So in the real world, either the null hypothesis is true or it's not true, it's false. One of those two options has to be true in the real world, right? So either men and women have the same IQ and the null is true, or they don't have the same IQ and the null is false, right? One of these two cases has to be the case. There's no other options. Now on the left side, we have the decision that we end up making based on our statistical test, right? We either get a significant result and we reject that null hypothesis, or we get a non-significant result and we do not reject the null hypothesis. Again, there's no other option. We either reject it or we don't reject it, right? So in total, these make up all the options here and these make up all of the options here. So let's say that we're going to start by looking at this case where, let's say in the real world, the null hypothesis really is true. There is no difference between our groups. But we had a weird sample and we ended up rejecting because our sample was so weird. We thought, no, there's no way that null hypothesis is true. And we rejected it. But in the real world, it is true. So when we rejected it, when it's true, that's our type 1 error. And we also call this alpha. So this is the same alpha we've been talking about of 0.05. Because remember, we're in charge of deciding like how much of a chance are we going to take that we're wrong here. And so science has said, 5% chance, that's pretty good. So we're saying when we're doing our statistical tests, we're saying there's a 5% chance I'm making a type 1 error and I'm rejecting a true null hypothesis. Now, if the null hypothesis is true and we don't reject it, that's our correct decision. It's true, we didn't get rid of it. Let me get my dogs out of here. Go. Sorry, dogs are playing, making a racket. Okay, so if the null hypothesis is true and we don't reject it, that's a good decision. We don't want to reject something that's true, right? So since if this is true, and these are our only two options, and this one is alpha, that means together they have to add up to 100% of the time, right? So this is our 5% of the time where we're going to be wrong, which means that 95% of the time we should be making the right decision. So to kind of illustrate, show a visual of what this looks like. So let's say we have these two groups or two populations. We have the blue population and the green population. The thing is, they're actually the same. The means, so if you imagine a number line down here at the bottom, their means going right up through the middle here, those means are the same thing, right? The means are equal. So this is the case in the world where the null hypothesis is really true. These two, if we kind of move the green one up or the blue one down, they would sit right on top of each other, right? So they are really the same thing. So let's take a moment and think about how we do this statistical testing, right? So let's say we're trying to determine whether these are from the same thing. So we establish our cutoff points, right? So here's my, sorry, pen's kind of wonky. So here's my cutoff point. So I'm going to say, if I get anything out here that's super weird, reject the null hypothesis. It's not true. So let's take a sample from our green guy, and maybe I get a mean that's a little bit off and it comes in like down here. So if we compare it, well, that's not weird. That's, the means are the same, and this is in our do not reject region, right? This is where we do not reject. Versus out here with our 2.5% on each side, these are our regions where we do reject. Right? So if we got a mean somewhere in here, we wouldn't reject that. And that's the right choice to make. This is the right choice because it's true. Those means really are the same in this case. Let's say we get a totally weird sample and our mean kind of ends up out here. So if we were comparing, this mean would fall in our rejection region, right? It's possible we could get a really weird mean. If our mean ends up in this rejection region, when the two populations are actually the same, then we're making a mistake. This is our mistake. It's a type 1 error. Because we're saying these two populations are different based on our findings, but in actuality, they are the same. So if we get something out here in this case, that would be a mistake if the null hypothesis is actually true. So we can think of it like this. So in terms of here, anything that lands in this middle section is going to be the right choice. Anything that falls in our tails, if these really are the same, everything out here is a mistake. We're making a type 1 error. I'm saying they're different when really they're not different. Okay? So that was assuming the null hypothesis is true. Now let's look at the alternative world, right? Different world, different question, something. In this world, we're looking at the case where in the real world, the null hypothesis is false. There is a difference. There is a difference there. Okay? So if there really is a difference and we reject the null and we say there's a difference, that's the same. That's right? There is a difference and we said there's a difference. So this is our correct decision. And this has a special name and it's called power. It's the statistical power that we have to be able to find a real effect. So if the null hypothesis is false in the real world, this means there really is a real effect for us to find. Yeah, there is something there. And look, we found it, right? Because we rejected the null hypothesis, we found the effect. Whoops. No. Let me try to go backwards. Nope. There we go. Okay, got it. Sorry, technical difficulties. So this is a good thing. Power is a good thing. It means there's a real effect out there in the real world and we found it. Right on. Correct decision. Now, just because there is a real effect doesn't mean we're going to detect it every time. It could be the case that we miss the effect, right? This is a real effect. And this is, we found it. This one is, we missed it. We did not find it with our data. So this case where there really is something to be found, but we did not find it, this is our type 2 error. And this gets a special name called beta. So whereas type 1 error is called alpha, like A, type 2 is called beta, like B. So again, this is the case where there is a real effect, but we miss it. That's an error. We're doing the wrong decision. So what does this look like in an example? So this is just one representation of what it might look like if the null hypothesis is false, right? So we've got our blue group and we've got our green group. And again, if we imagine we've got some number line down here, well, the mean of our blue group is over here, right? That's our mean 1. And the mean of our green group is over here. That's our mean 2. Those are clearly not the same mean, right? They're different. They're not going to be right on top of each other if we put them in the same row. So this represents a case where the null hypothesis is false. There is a difference between our groups. So again, we sort of have these we have our rejection regions, right, that we use, where we've got our 5% and our 5%. So if we get anything in one of these rejection regions, we're going to reject the null hypothesis. And that's the correct decision because, like it says up here, the null hypothesis is false. It's not true. So we want to reject it. Now, how this works out is that basically anything that falls in this rejection region, this is all going to be the right decision to make, right? Because we want to reject. So if we get anything out here, our mean is here, reject, they're different. Our mean is here, reject, they're different. Our mean is right here, reject, they're different. All those are the correct decision, right? That's the right decision to make in this case. Let's say we get something this way, right? So I get a mean that's here. Uh-oh, that's in my do not reject zone. Whoop, reject. I can spell, guys. Go back. There we go. Spoilers. So if we get anything over here, we're not going to reject the null, even though we should, because it's not right. It's false. So anything we get over here in our don't reject region, this is a mistake. This is our type 2 error. So basically anything over here, this is our type 2 error. Whereas here, this is the right decision. There is a difference and we did find a difference. This represents our power of our test. So I'll show you a little nicer looking version. There we go. So we see the power that we have is where we are correctly rejecting. Type 2 error is where we're incorrectly not rejecting. Right? I know there's lots of double negatives going on, but we're incorrectly keeping the null hypothesis when we should be rejecting it. Now, if let's say that these curves are a little closer together, right? We're talking about that effect size again. So in this case, the effect size was, that looks pretty big. There wouldn't be a lot of overlap between those two curves if we put them in the same row, right? This blue one would be over here. So what if they were closer together? The effect size is smaller, right? What does that do for us? What happens? Well, if we're drawing in our rejection regions, you can see what happens since they're closer together here is that our power goes way down and our chance of making a type 2 error goes way up, right? If we compare that to this guy, this had a lot more power. This one, our rejection region, our chance of making the right decision is much smaller, and our chance of making the wrong decision is much bigger. So this shows us that if our effect size is small, then we only have a little bit of power. If our effect size is small, we have a little power and a lot of chance of making a type 2 error. If our effect size is really big, we're going to have a lot of power and a smaller chance of making a type 2 error, right? So we could imagine even another case where maybe that curve's way out here. Well, then basically everything we would be able to detect, right? So if there's a humongous effect size, then we're going to have a massive amount of power. We're very, very, very likely to be able to find that effect if it's a really, really big effect. If it's a really, really small effect, like they're only just a little bit different, then our power is going to be really low. So we'll come back to that idea because power is affected by a couple things, and one of them is definitely the size of the effect. Now there's a kind of analogy that a lot of people use. It sort of helps them understand this idea of type 1, type 2 a little better. So if you're more legally minded or like me, a true crime junkie, then this may make more sense to you. So again, we have the true state of the world. So imagine we have a murder case. Either the defendant did not murder the person and they're innocent, or they did murder the person and they're guilty, right? It's not like you can half murder somebody. So they either murdered them or they didn't murder them. One of those has got to be true. The jury is going to return one of two verdicts. They're either going to say they're guilty, they did it, lock them up, or not guilty. Whoop, spoilers. Not guilty, let them go. So let's assume the defendant is innocent. They did not commit the murder. But for whatever reason, the jurors are like, this guy, I'm pretty sure he did it. He's guilty. That's a wrongful conviction. That's a mistake, right? The person did not commit the murder, but he's being locked up for it. So that is a type 1 error. That's a really bad mistake to make, locking up somebody who didn't do the crime, which also means the person who really did do the crime is out there wandering the street still. Okay, so that's bad. Now, if the defendant was innocent and they said not guilty, that's good. Those two things go together. That's a correct acquittal. They didn't do it and they didn't find them guilty. That's good, right? That's right. Now, let's say the defendant really is guilty and they find them guilty. Guilty, guilty, correct conviction. Boom, that's good. This is our power. That's the ability to be able to detect that they really did do it. Your evidence was strong. You found the guilty person. Now, if they're guilty, but the jury returns not guilty, again, that's a mistake. They're letting the guilty person go, right? So that's what we call a wrong acquittal. They were acquitted, but they shouldn't have been because they did the murder. That's equivalent to our type 2 error. So type 1 error is saying they're guilty when they're not guilty. Type 2 error is saying they're not guilty when they are guilty. You missed their guilt because your evidence wasn't strong enough. Generally, type 1 is considered worse than type 2. And so if you think of this in terms of the legal system, with a type 1 error, not only is the real murderer free, because that's what happens in type 2 errors, the murderer is free, but here the murderer is still free because you didn't lock up the right person and you put an innocent person in prison, right? So that's almost like extra bad compared to, at least here you didn't lock up somebody who didn't deserve it, right? In type 2, just the guilty person is walking free, but you're not locking up somebody who's innocent. That's considered less bad than our type 1 error. Okay, so and that's why we say type 1 error, we're only going to do that about 5% of the time. We want to make that number pretty small to make sure we're not saying there's something there when nothing is there. This also very much relates to medical trials, the medical field. So type 1 error is sometimes referred to as a false positive because they're saying, I found something when there's nothing there to find, right? It's like having a man who's always been a man, saying you're pregnant. Physically impossible. There's no way he can be pregnant. So that's a mistake, right? That's our type 1 error. I found a baby in you and there's no baby in you. Okay. Type 2 error is sometimes called a false negative. It's the case where someone really is pregnant or they really have the disease or whatever you're talking about. I'm not saying that pregnancy is a disease, but you get it. So if they really have the thing, they really have the baby or whatever, and you don't detect it, then you're missing it. You're missing the effect, you're missing the baby, you're missing the disease, you're missing the whatever. That's a false negative. You're saying, nope, not pregnant when this lady is clearly pregnant. Okay. So those are our type 1, type 2 errors. So power, how this all sort of connects, right? So in terms of how we calculate power, we're not going to learn like by hand formulas for calculating power. Honestly, what people usually do is they go online and they get a power calculator. And a power calculator lets you put in what type of statistical test you're doing. Are you doing a t-test? Are you doing a correlation? Are you doing an ANOVA or chi-squared? Those are ones we're going to cover next. So what are you doing? What size is your sample? What is your effect size? And what's your alpha level? What's your tolerance for a false positive? You put all those things in and it will tell you this is your power. Okay. We also can use power calculators to help us determine what's the best sample size to use for a study so that we make sure we have enough power so that if there is an effect, we can really find it. Because we don't want to do a whole big study where we get a lot of data and we spend a lot of time and money and maybe we're paying people and effort and then we miss something that's really there. So we want to make sure, how many people do we really need to be able to detect this effect that's out there? So that's where power comes in handy, right? Because there are 3 major things that affect power. Number 1 is how big is your correlation or your difference? How big is your effect size? If you've got a really, really big effect size, it's going to be easier to find. That means your power is going to be higher. If you have a very, very small effect size, it's going to be harder to find. You're going to have lower power. Another thing that affects our power is how many people are in your sample. So remember that when we're doing our z-scores and our t-scores, sometimes we're dividing by the standard error, right? And the standard error looks something like this. It's sigma over the square root of n, or it's s over the square root of n. So the bigger that n is, this is meaning that our sampling distribution is getting skinnier and skinnier the more people we have in our sample. So if our distribution is getting skinnier and skinnier, then we're going to have more and more chance of being able to identify a true effect, right? And so the more people you have, the more power you're going to have in your study. If I did a study with 5 people, I'm probably not going to find a significant effect, no matter what size that effect is. If I do a study with 5,000 people, I can probably detect an effect that's even really small because I just have so much power because I have so many people that I'm going to be able to detect everything. You can also technically increase your power by decreasing your alpha level. So if we go way back to one of these guys, right? So here, if we made this alpha level bigger, if we moved that guy and we said, I'm going to make alpha here instead, this is going to be my rejection region. I'm making my rejection region really, really big. Then that would also mean that we have more power, right? Because there's more chance of making that right decision. So you could technically increase your power by increasing your alpha. The problem is, like we said, alpha is usually considered the worst mistake to make. We definitely don't want to make an alpha type 1 error. We would much rather make a type 2 error than a type 1 error. We'd rather miss it than say something is there when it's not there. So in practice, like in theory, you could do that. In practice, we do not do that. It is not practical to change that alpha level to be bigger, because that just means you got a way bigger chance of making a type 1 error. And science journals do not want you to be making a type 1 error. They will not accept your study if you're using a big alpha. They're going to be like, what? This could easily be a type 1 error. Okay. So 3 major factors: effect size, sample size, and your alpha. So, like I said, to calculate statistical power, or why do we care about statistical power? It's really helpful to help us calculate the sample size that we need when we're planning a study. So you can do calculations ahead of time by sort of estimating what your effect size might be. So maybe you're like, let's say we have a medium effect. How many people am I going to need in my study in order to detect a medium effect? Or you could be like, there's probably maybe it's not that strong of a relationship. It's only like a R equals 0.3. How many people am I going to need in my study in order to make that 0.3 statistically significant, so I really find it? So this is the way that most people use power analysis for, is to determine what should your sample size be before you go out and start collecting data. Some people also calculate power after they're done with their study. Like they did a study, it was not significant, and they're like, dang, that's not what I was hoping for. I wonder if I didn't have enough power, right? So then they can do a power analysis, and maybe they find that they only had like 40% power. That's really low. They only had a 40% chance of finding that thing. So then they're like, okay, well, maybe there is no effect, but maybe I just didn't have enough people in my study to detect the effect. Right? That is a very common way that power is used as well. So I'm going to end with a little analogy, this sort of game, hypothetical game to play, to hopefully kind of illustrate more clearly this idea of power with effect size and sample size. So let's say that I hid a quarter in a football field. And I'm out there and I've got my stopwatch and I'm like, I will give you 5 minutes to find this hidden quarter that's somewhere in this football field. And if you find the quarter, you win $1 million. You got 5 minutes. I don't actually have $1 million to give away. This is not a real contest. There's no quarter in the football field. But let's say there was. Okay. How good do you think your chances are? You got 5 minutes. There's a quarter somewhere out there. How good do you think your chances are you're going to find it? You think you're very likely to find that quarter in 5 minutes? Or you think probably not, right? Think about your chances. Probably not great chances of finding that quarter. Wouldn't it be nice if I said, you can get some friends and family to help you if you want, you can get some people to help you look for that quarter. More people, more chance to find it, right? How many people would you want to help you find? Maybe you're going to invite your 50 closest friends, right? Or however many people, right? If you get everybody lined up that 5 minutes, you're pretty guaranteed to find that quarter if you have enough people, right? But there's a catch. So I tell you, you can get as many people as you want to help you, but then you're going to have to split the $1 million with everybody. Right? So then maybe you're like, okay, maybe not my 50 closest friends, maybe like my 10 closest friends, right? Because then you still have a pretty good shot at finding a quarter with 10 people for 5 minutes, but at least that way you're still getting $100,000, right? You don't want to give away all the money. So it's kind of this balance. How likely do you think you are to find it? And then the more people you have, the more likely you are to find it. But there's always a cost associated with that. So that's the quarter. Now, let's say I call somebody else up. We got a new contestant. I hid a full-size, regular, real elephant somewhere in this football field. I'm talking like an Asian elephant is out there. I'm going to give you 5 minutes to find this huge elephant. And if you find the elephant in this football field, you'll win $1 million. How likely do you think you are to find the elephant? We're talking like a big, I don't know how much elephants weigh, but like 2 tons or something, right? Elephant. Probably you're going to find the elephant, right? You think you need help finding the elephant? Knowing that everyone you get to help you is going to get an equal share? I'm guessing most people are like, no way. I can see that elephant. I'm getting the $1 million, right? It's a huge elephant. You're going to see it in a football field. You don't need a lot of people to help you. So this is really kind of illustrating power. How likely are you to find that thing that's hidden somewhere in the field, right? So we know that there are 3 major things that affect power. We've got the effect size. How big is the thing? How many people are there? How many people are in your sample? And your alpha level, okay? So in terms of our game, the elephant versus the quarter, the effect size is the elephant or the quarter, right? It's the size of the thing that you're looking for. A quarter would represent a really small effect. There is something out there, it's just really, really small. So in that case, you're not going to be very likely to find it on your own. The elephant represents a really big effect size. You're very likely to find that guy. The N is sort of like, how many helpers do you have helping you, right? So if you have more people in your sample, the more likely you are to see the effect. Just like if you have more people helping you look for that thing in the field, you're more likely to see it, right? Your power goes up as your N goes up. And finally, what is our alpha? I'm sorry to break this one to you, but I'm not really sure what alpha is in this case. It's not a perfect analogy, but hopefully you sort of get the point between, like, we're talking power here, right? Your power is how likely are you to find a thing, and if the thing is big, and if you have a lot of people helping you look for it, you're really likely to find it. So with big effect size and lots of high sample size, your power is going to get bigger. So that's all I've got for you. I will see you soon.